So looking back at the dining philosophers, as we said, it meets all the conditions for being in a deadlock, and there are multiple ways to break that deadlock. One of them is basically to have an extra chopstick, for example, in the middle of the table. One of them would be, so if you can add some extra resources, you can change it such that you need to pick two chopsticks at the same time, and if you don't, put down whatever you have picked. Um, you can change it by just moving one of the chopsticks from the left hand side of one of the philosophers and putting it in the middle of the table, and that basically and have still the rule that to pick the left hand side one first, so that philosopher has no longer a left hand side one, and have a rule that if you are not able to pick both sides at the same time, so sorry, if you don't have two chopsticks, you try to grab the one in the middle. So there are multiple ways to break that deadlock, as we say. There's the communal dining philosopher's problem, and that you have basically instead n chopsticks in the middle of the table, and n philosophers each can take one chopstick at a time. And then you can have, for example, a rule that basically says that I pick a chopstick as long as it is not the last one in the middle. That basically means that if you have n chopsticks and in the middle of the table, and each one picks one, and but checks also how many are remaining on the table, and if it's just one, then he leaves it, then that will basically break also your deadlock. And you can reflect on this as different ways to actually implement free locking mechanisms in your system. So communal mutant dining philosophers is that you have n chopsticks at the middle of the table, and philosophers each take one chopstick at a time, but you need k chopsticks to eat, where k is greater than 1, and k can be 3, for example. And then you will basically implement it such that, well, going back to threads, suppose you have n threads that will need each 3 locks or something to proceed. Then you will implement the same mechanism by basically saying that I take one, and I do not take one if the remaining ones is less than k minus 1. So if I need 3 chopsticks to eat, I'll pick one as long as there are more than 2 chopsticks on the table. Okay? So that way you basically will end up with, again, a possibility of another deadlock, which basically is that you might end up in a situation where 2 philosophers have 2 chopsticks and 1 less sufficient, right? But then you add also that I will not pick it if it's less than 2 also. So if somebody picks if somebody picks one of the 2 that are remaining, so if everybody picks one as long as there are more than 2 on the table, okay, and no one and you do not pick the last one unless you have 2 already, okay. So you cannot end up in a situation where with a deadlock again. There are methods that tries to predict the future, and one of them is Banker's algorithm, which basically tries to state the maximum resources needed in advance. So you as a programmer, you try, or you basically make the program try to predict the maximum resources needed in advance. And you allocate resources dynamically when they are needed, and wait when your granting requests lead to a deadlock. So this is different from just blind allocation in the sense that it has an extra optimization layer. So you basically say that, okay, I need this much amount of memory and these 3 locks and these data this data to basically proceed from the very beginning. But then you do not get allocated this blindly when you start, but rather you basically start by whenever you start your operations, you set a flag that you're starting, and these are things that you're going to need, and then any future thread that tries to start will check if when it starts it can lead to a deadlock. Yeah, so and requests can be granted if you have a way out of a deadlock, basically. And you grant requests if and only if they result in a safe state, and the sum of the maximum resources needed to current threads can be greater than the total resources. So, so you can proceed basically, and you can proceed even with more resources being allocated in theory to threads than are available, but you still have a way to finish, maybe by blocking some operations. So an example is that you proceed if and only if the total available resources minus the number of allocated is greater than the maximum remaining that might be needed by the new thread that is starting. And that basically guarantees that this thread can finish, although it will have to wait for some of the other threads to finish in the beginning. And this is how it looks like. So you have some initializations of the value of the different variables you check when you're doing the resource, the thread scheduling, and that's basically you pick the number of resources, number of threads that are going to run, the available resources, you have them in a list, the maximum usage of resources I needed by any thread. So you basically have an availability matrix for all different resources that are contended. So, and that availability can be of one, right? So you can have only one. So if for some of the values, so if you're, for example, doing the value plus the increment code we have been looking at earlier, then your availability of this resource is one because you just have one counter in this case. While in the case of that, if you in the case of this particular case, you have just single variable, but imagine that you have multiple variables that are dependent in some way. So you can have an availability of that resource of one, right? And then you basically, for each thread that is entering, you have the Emacs dictionary sort of, or map that basically says, or double array that basically says that the maximum amount of resources I needed by thread J, and if that resource has just one in availability, then no thread can, for example, require two of it. So you cannot require two of the value parameter in the increment function, right? Because there's just one counter there. And then you basically have an allocation double array or matrix or map or dictionary. I mean, the implementation can differ based on your programming language. And then you basically have code that checks once you get a request, which is the code lower. I mean, the bottom half of the of this slide, which is basically a code that checks when a request arrives if there is enough capacity for this request. And if there's enough capacity, this request is basically a thread. Then it will schedule it. If not, then it will not schedule it. And you start by basically acquiring a lock, checking that it's safe to proceed. If it's not, then you break. And while it is safe, then you basically while it is not safe, you basically block and do nothing. Versus if you if it's safe, then you basically start allocating the resources, and when you do the allocation, you basically change all the different parameters that you have defined earlier in your class. For example, the allocation map or the allocation array, you basically change the resources allocated to the thread by increasing the number of it, and you decrease it from the available resources, and then you basically again assert that things are safe still, and you release the lock. And then isSafe is basically a function that or a procedure that goes through all the threads that you have, all the resources that you have, and all the available resources that you have, to basically see if there is a possibility of a deadlock. And that is basically by making sure that there will be eventually enough resources for a thread to continue. Otherwise, it will just break, right? And you can see that in doing that, so in doing this check, basically, you try to see if there is enough available resources now or in the future that, for example, the lock is going to be released in the future. And then you have a function that is called would be safe, that basically checks for if the lock would be safe in the would be released in the future, so that you can acquire it, or if the resource would be released in the future, so that you can acquire it. And the way it does that is that it hypothetically decreases. It hypothetically simulates the case when you basically remove one of the threads, and checks what would happen to your threaded program, basically, in that case, to if you add the new thread. The final way to manage deadlocks is basically to try and detect and repair. You basically shoot a thread to make sure that it gives up resources if you end up in a deadlock. So you pick a thread that is currently also holding your resource allocation, and you just kill it. Okay, which is the easiest way. And in the Dining Philosopher's problem, that would be by removing one philosopher, killing him, or doing something that's kind of mean, but that would break the deadlock. So this is not always easy, because with a mutex, for example, you cannot just kill a thread, because everything will be in a non-consistent state, unless you basically have written a very clean exception handling code in your program. So there are also other ways. One of them is basically that you simulate that everything will be fine. I'll just continue and think that nothing will happen. Okay, it's kind of similar to the RCU locks, where you basically go on reading and saying that things will happen. It's mostly used, or not mostly, but in many cases it is used in large distributed systems to just get the system outside of this state. This is again not a very wise idea generally, because you might end up, especially in operating systems, this will basically kill your operating system, because you'll probably end up in, you defeat the purpose of locks in that case. If you just continue thinking that, oh, there's nothing wrong with me continuing, you will end up with a very unstable operating system. So you don't do that in operating systems. You do that more for operations where you don't really care if what will happen if the state is not consistent. The third way is to try to roll back actions of the deadlocked thread. So you basically try to remove the thread, and so if a thread has acquired some resources in some sequence, then you start releasing the resources in an opposite sequence, so that until the deadlock is broken, basically, and then maybe lock So for example, if you're looking A B and the other one is looking B A, then you basically are you'll be waiting for look B to re get released. So you basically will roll back. So you have not been able to lock A anyway because lock A was acquired, so you just roll back from lock B, and that should be it. And that would require your system to actually know a bit of its history. And this is actually used in database systems, and it's easy in database systems to do that. Not very easy, but easier than in operating systems. And the way that the algorithms for this work is that they scan for graphs. So you scan basically your system to try to detect cycles in your system. Uh, and in that case, you basically can try to break your cycle. These are basically the ways that you would use to detect and repair a deadlock.